Hi, welcome to this video. I'm going to review the chapter 8 of this special publication of economic geology. The title is Uncovering the Missing Magmatic Link for the Tongkuangyu Porphyry Copper Deposit, Trans-North China Orogen, Implication for Porphyry Copper Deposit Model and Exploration. You know that most of porphyry copper systems are Phanerozoic, they're geologically young. So when geologists stumbled across a porphyry system dating back 2.1 billion years in northern China, it raised an eyebrow to figure out when and how the copper mineralization at this deposit happened. The researchers used zircon dating. They took rock samples from different layers around the deposit, including volcanic tuffs, granodiorites and altered schists, and analyzed the tiny zircon crystals inside using laser ablation. They also looked at hafnium isotopes in the zircons to see if the magma had been influenced by older surrounding rocks or not. This helped them spot the difference between original magmas and ones that had been contaminated by older material. In short, they used zircon ages and isotope signals to piece together the timing of magmatism and mineralization, and they found strong evidence for a no hidden magma chamber that likely powered the copper system in this area. This is a regional map, shows the northern Zhongtiaoshan region. It's an ancient belt of crusts welded between major tectonic zones in northern China. The Tongkuangyu deposit is marked here, and it's hosted in Paleoproterozoic granodiorites and volcanic sequences. But what makes this area so fascinating is the timing puzzle it presents. When geologists dated the host rocks, they came back at around 2.18 billion years old, but the copper mineralization formed closer to 2.09 billion years old. So there's almost 100 million years time gap, and it's a huge gap in geological time. So this raised a big question: if the rocks holding the copper are not the ones that formed it, then where did the mineralization fluids come from? To solve this, the team used, as I said, zircon dating and hafnium isotopes, like time stamping and fingerprinting magma batches. They found younger volcanic rocks, basaltic and andesitic tuffs, with zircon ages that match the copper event, and it suggests no eroded or buried 2.1 billion years magma chamber was responsible for the fluids. In other words, the system that formed the ore is no longer visible, but its signature is still recorded in the rocks above it, and that's huge for exploration. It means that ore forming magmas don't always leave behind obvious igneous intrusions. Here is another map at mine scale. When I first read this article, I was curious at why the dating results were surprising and why they compared the mineralization with volcano-sedimentary host rocks. And then I realized that early interpretations assumed that mineralization was stratobound, possibly sedimentary exhalative, SEDEX, or syngenetic. So magmatic hydrothermal was out of question. There was no clear porphyry intrusion at the surface, no stock, no dike swarm, no visible intrusive center. So without any smoking gun, early researchers didn't realize they were dealing with a porphyry-style copper system. But now we know that this is a porphyry system, just a really old and heavily modified one. So what are the red granodiorites doing here? You can see that there are some granodiorite porphyry units in red, which are folded and deformed during metamorphic events. They're part of the older crustal architecture in this area, and they're possibly served as wall rocks or roof zones above the real porphyry system. And their foliation and deformation make them a good pathway and trap for ascending mineralizing fluids, but they're not the causative intrusion. Maybe just bystanders that got mineralized in the process. Here is a summary of key features of the host rocks, alteration and mineralization. So we have a 50 to 200 million years gap between emplacement of the host rocks and copper mineralization. In contrast, in Cenozoic porphyry systems like those in Chile, Peru or Indonesia, the mineralization usually occurs synchronously or just a few million years after the causative porphyritic intrusion. An interesting point to me here was that hydrothermal overprints, chlorite and quartz, they occurred much later, around 1.8 billion years, which shows prolonged or multi-phase fluid activity is interpreted as a post-mineralization hydrothermal overprint associated with regional metamorphism during the probably Zhongtiao orogeny. So they're not related to the main mineralization event at 2.1 billion years, and it shouldn't be mixed up with the porphyry system. So potassic alteration, biotite plus minus K feldspar here, is the only definitive porphyry style mineralization. And the rest of alterations, cersite, albite, chlorite, they're all post-mineralization overprints, likely due to regional metamorphism and deformation, rather than porphyry-related hydrothermal activity. Here we have geochemical plots for comparing the 2.09 volcanic tuffs at Tongkuangyu to typical Phanerozoic porphyry-related magmas. In panel A, we have primitive mantle normalized trace elements. The study area, Tongkuangyu, shows strongly LILE enriched rubidium, barium, thorium, uranium, and HFSE depleted niobium, tantalum, and titanium, and shows distinct negative niobium, tantalum, and titanium, which are typical classic arc signatures. and they're consistent with subduction-related magmatism. They show strong phosphorus and strontium troughs, which suggest significant plagioclase fractionation or alteration. And pattern falls well below the older 2.18 billion years rhyolite and granodiorite units, indicating a different magmatic lineage, younger and more evolved. Phanerozoic porphyry-related suits, which are for comparison, they show same arc signatures. They are niobium tantalum depleted, LE enrichment, and they often also show strontium and europium anomalies because of plagioclase and amphibole fractionation. So you can see that Tongkuangyu is chemically consistent with Phanerozoic arc porphyries despite its age. On the right we have panel B, which is chondrite normalized rare earth patterns, and Tongkuangyu shows light LRE enrichment, moderate slope with lanthanum to lutetium. It shows slight negative europium anomaly, suggesting plagioclase removal. And overall pattern is flatter than the 2.18 billion years units, but shows no sign of heavy RE enrichment or depletion, and suggests no strong garnet influence and probably shallower melting conditions. In the modern porphyry magmas, they also display LRE enrichment and variable europium anomalies depending on magma depths, oxidation state, and crystal fractionation. So study area's pattern is again well within the compositional range of arc-related porphyry magmas. So what are the key comparison takeaways? Despite being Paleoproterozoic, the 2.09 billion years volcanic troughs at Tongkuangyu show trace element and rare earth signatures that strongly resemble Phanerozoic porphyry systems. And what's unique here is that the older 2.18 billion granodiorites look more evolved and crustal, and they're not the source of the mineralizing event. We can find the same situation in Yerington, Nevada, in which we have a Jurassic arc, and the lower hill granite is a large granitic evolved and barren pluton. And in contrast, the copper molybdenum mineralization is associated with less evolved porphyritic intrusions. So here geochemistry confirms that younger arc-type magmas, not the older host rocks, were responsible for copper delivery and support the zircon, and they're supporting the zircon and hafnium isotope evidence of no hidden porphyry source. Another key point is this in this diagram is that 2.09 basaltic to andesitic troughs, they are the closest preserved volcanic expression of the porphyry system. So at Tongkuangyu, they were likely fed by deeper, now eroded or maybe unexposed porphyry intrusion. Here we have zircon uranium lead concordia diagrams. Usually in phanerozoic porphyries, uranium lead zircon ages often show a tight cluster centered on the intrusion's crystallization age. They usually differ around plus minus 1 to 2 million years, and they show a single short-lived magmatic event with those tight dating results. And here we can see that at Tongkuangyu, especially in the basaltic andesite tuffs, we have two zircon populations, group 1 and group 2, which are younger, and the later group is coincides with copper mineralization. So this suggests a complex magmatic history, likely involving zircon inheritance or mixing of melts with older crustal input. And actually the authors in this article acknowledge the presence of older inherited zircon cores. So here's the conclusion and key insights from this article. Tongkuangyu deposit tells us a deep story. One of what we can see, what we almost missed was that the host rocks are too old, the intrusions are too evolved, and the causative magmas are long gone or eroded away. But clues were there in zircon grains that carry the memory of a younger, more primitive melt, and in isotopic fingerprints, hafnium values that pointed to mantle input, not crustal recycling. And we can see in the alteration zones that preserved the structure of a porphyry system, and even without intrusion itself. So this wasn't just about finding copper, it was about chasing a 2.09 billion years old ghost porphyry through layers of overprint, inheritance, and time. And it worked by pairing high precision zircon dating with hafnium isotopes, alteration mapping, and tough sampling. The team here pieced together a porphyry system that no longer exists at surface. Thanks for watching.